Hi, this is the fourth lecture in the series on sequences of functions. As I said in the last lecture, we are going to deal with some theoretical results. Essentially what we plan to do is we are going to restrict our domain to be subsets of R, possibly intervals, and we are going to look at functions which are continuous or integrable, and we'll also assume if the sequence Fn of continuous function converges uniformly to F, what can I say about F? And similarly, if I have sequence of integrable functions, but that I will do later, okay, and integrability also we want to look at. Then maybe we also want to talk about differentiability. Okay, these are the few questions we want to deal with. Okay, so we will go one by one. Okay, I'll do the easy ones first, okay, before we go to the tougher ones. Okay, so let us start sharing the screen and do that. So notice that our example, okay, like Fn of x equal to x power n on the closed and bounded rule 0 1, and Fn's are continuous, and we also know Fn converges to F pointwise, where f of x is 0 for x less than 1 and equal to 1 if x equal to 1, right? Then f is not continuous, right? Okay, so what we want to say is this kind of phenomenon cannot happen if the convergence is uniform. What do I mean by that? Let us start with a subset, okay, J of R. This is just a subset, non-empty of course, okay, and suppose Fn's are continuous functions from J to R, and assume Fn converges uniformly to F on J, then F is continuous on J. This is what we want to prove. Remember, J need not be any interval or anything, because if you had followed my lectures on continuity, I had defined continuity of functions on any arbitrary subset of R, not necessarily intervals. But if you are uncomfortable, if you have not seen those lectures, you can assume J is an interval, okay, but that doesn't matter. Okay, this is what we want to prove. Is the theorem clear now? So Fn's are continuous for all n, and Fn converges to F uniformly on J. Then I want to claim F is continuous on J. Yeah, okay. So how do I prove it? So if I want to prove F is continuous on J, what does it mean? I have to say F is continuous at each and every A in J. So fix A in J, then I have to say F is continuous at J, continuous at A. Yeah, if I want to prove F is continuous at A, what is that I have to do? I have to estimate mod Fx minus Fa. Yeah, if you had been a follower of my lectures on analysis, you will know that anything is something or other you have to estimate in analysis. So to prove continuity of F at A, then take points near, this is my A, take points in X, which are X is also in J and X is near, okay, near A. Then I have to estimate this. Do I know how to estimate? I do not know how to estimate. What do I know how to estimate? Remember, Fn converges to F uniformly. In particular, I know how to estimate Fn of x and minus f of x. Similarly, I know how to estimate Fn of A minus f of A. Do you understand this? Yeah? So, somehow I have to bring in these things. So what do you think I will do? We will use some kind of a curly leaf. Right, add and subtract. So what we will do, I will write as Fx minus Fnx. Since I have subtracted, I have to add Fnx, okay, and Fa I have to add, do Fna minus Fa. Therefore I can subtract Fna plus Fa. You understand this? Yeah, this is clear why I wanted. This is clear why I wanted, because there is a minus A, that means I have to take Fna minus Fa, right? and since I subtracted, I have to add. Since I added, I have to subtract. Is it clear? Okay, this is equality actually. Then what do you think I will do? I can write triangle inequality, that is fx minus fn of x plus fn of x minus fn of a plus fn of a minus f of a. Okay, so far I have not used anything to do with n, epsilon, nothing. This is just a triangle inequality. You got it, right? Now what do I want to say? I want to say this is less than epsilon if the x is in j and the distance between x and a, that is mod x minus a, is less than delta. That is at the back of my mind. You follow that? So I want this to be less than epsilon. So what is the easy way? As I said in analysis, I want to show this is less than epsilon, but this fellow is less than or equal to sum of these three terms. So if I show sum of these three terms is less than epsilon, then this will be less than epsilon. Okay. For that, what I can do is, if I show each one of these terms is less than epsilon by 3, epsilon by 3 and epsilon by 3, there is no need it has to be epsilon by 3. It could be anything. It could be epsilon by 4, epsilon by 4. This may be epsilon by 2 also. Anything is okay. You understand? But the sum should be epsilon. You understand? I want to do that. Now can I do that? Okay. Remember, fnx converges to fx, right? Therefore, if you give me epsilon by 3, I know there is an n. So that for all n greater than or equal to n. But remember, for this n will also keep varying. This may depend on a, this also may depend upon x, and x also keeps varying, right? But what do I wanted to show? I wanted to show fx minus fa, right? And for all x near to a, right? Therefore x will keep varying. So what do? This is where you use uniform continuity. Since fn converges to f uniformly on j, given epsilon by 3, there is an n, so that for every n greater than or equal to capital N, mod fn of x minus f of x is less than epsilon for every x, because this is where we need the uniform convergence. You understand this? Therefore, if I choose my n greater than or equal to capital N, okay, so in particular take n equal to capital N, what do I know? This will be fx minus f suffix capital N of x. This will be less than epsilon by 3 because x is in j. Now a is also in j, therefore this third term is also less than epsilon by 3. You understand that? So what I am doing is I am fixing in n now. Fx minus fa is less than or equal to fx minus fn of x plus fn of x minus fn of a plus fn of a minus f of e. You understand this? Now for any n, whatever I wrote is correct, but since I want to prove each of those terms is less than epsilon by 3, I am using uniform convergence to look at the first and third term. They can be estimated, right? So in particular take n equal to capital N, this will be less than epsilon by 3. This will also be less than epsilon by 3. You understand that? This is true for every x in j. But I want this to be less than epsilon by 3. How do I make it? Remember, that is why the reason why I have to fix capital N. I am not allowing little n to vary. Fix that to be capital N. Now look at fn. That's a fixed function. Okay. What do I know about fn? Fn is a continuous function from x to j to r. Right? Now what do I know? I know fn is continuous on j, therefore fn is continuous at a. Yeah. Therefore, if you give me an epsilon by 3, I know there is a delta positive, so that for all x in j and intersected with a minus delta to a plus delta, what do I know? Fn of x minus fn of a will be less than epsilon by 3. That is by continuity. You understood that? Do you also realize why I have to fix capital N? I am not allowing n to vary, because if I allow n to vary, then this corresponding delta may also vary. Yeah? Okay. Now keep it. So what do you think I have done? So now I can write a textbook proof. Okay, I think I have proved it, but I would like to write a textbook proof. How will I do that? Given epsilon, okay, using uniform convergence, there is an n, so that for all n greater than or equal to capital N, and for all x in J, f1 of x minus f of x is less than epsilon by 3. This is one. Okay, and second, f1 continuous at A, therefore there exists a delta such that 0 less than mod x minus A less than delta, and x is in J implies mod fn of x minus fn of A is less than epsilon by 3. This true circle. You understand that? Yeah, therefore for x in J intersected with A minus delta to A plus delta, what do I have? Mod fx minus fa is less than or equal to fx minus f capital N. Because remember, here there is no necessity for which n. This is true for any n, but we are fixing it. f1 of x minus f1 of A plus f1 of A minus f of A. So this is epsilon by 3, epsilon by 3, this is by 1, and this is less than epsilon by 3 by 2, by 1, this is also by 1. You understood that? So what do you think I have proved? The limit function f is continuous at A, and A was arbitrary point of J, therefore f is continuous on all of J. Is the proof okay? Yeah? Pause, review, proceed. Okay, so let us look at what is that we have proved. We have proved if f1 converges to f uniformly and if f1s are continuous, then f is continuous. Okay, where whatever the domain, okay, on J, right? Okay, so this most often this is used to prove some convergence is not uniform. How do I do that? Suppose I have sequence of continuous functions, and suppose f1 converges to f pointwise, but f is not continuous, then f1 does not converge uniformly to f on the interval on the set. Do you accept it? Why? Because if the uniform continuous, f must be continuous. But the hypothesis f is not continuous, therefore the convergence is not uniform. Do you follow that? In fact, in many textbooks, this theorem is what used to prove. If I look at this example, fn of x equal to x power n on 0 1, then we know the f1 converges to f, and we know what is f. F is 0 on 0 1 and equal to 1 at x equal to 1. So the f is not continuous, right? Therefore f1 does not converge uniformly to f on 0 1. Okay, this is a usual proof you will find in many textbooks, and in fact you ask any teacher or any of your seniors, immediately this is a proof they will give. Okay, what is the question you should ask? Consider the function f1 of x equal to x power n on the closed bounded interval 0 1. Okay, does it converge uniformly on the closed interval 0 1? They will immediately say no, because the limit function is not continuous, right? But let's look at the same thing, f1 of x equal to x power n on the open interval 0 1, then I know f1 converges to 0 pointwise, right? Now the now the f1s are continuous on 0 1, and the limit function, this is your limit function, that's also continuous on 0 1. Can I conclude f1 converges to f uniformly? No. We already know this is not uniformly convergent on the open interval 0 1. Do you understand this? Please pay attention. This is something very crucial, right? Therefore, the theorem we proved is a sufficient condition. What do I mean by that? Okay, if fn's are continuous and if fn converges to f uniformly, then f is continuous. But it may happen fn may converge to f non-uniformly, that is, it may converge point-wise but not uniformly, but still f may be continuous. The example is x power n on the open interval 0 1. Okay, pause, review, proceed. Okay, next question we want to look at is the thing. Now let J be an interval. Okay, and fn's are continuous function from J to R, and let us assume fn converges to f uniformly on J. Then by the last result we know f is continuous on J. Yeah, therefore I know, let us also assume the interval is AB, right? Since fn's are continuous, we know that they are Riemann integrable. Interval a and fn t dt exist, and since the limit function f, since fn converges to f uniformly, the limit function is continuous, therefore interval a to b f dt also exists. That is, fn's are integrable, f is also integrable. What I know is fn converges to f uniformly, so I want to know whether integral of fn converges to integral of f on the interval ab. Is the question clear? Yes? Yeah. So question is integral a to b fn t dt, does it converge to the real number a to b f t dt? Notice that this makes sense because fn and f are continuous, therefore they are integral on the interval ab. Yeah, to show this sequence of numbers converge to this number, what is that I have to estimate? I have to estimate this a to b fn of t dt minus interval a to b f of t dt. I want to show this is less than epsilon. Okay, this epsilon etc will come later, don't worry about it now. Okay, the first thing I will notice is integral is a linear map, that is, integral of f plus g is integral f plus integral g. Therefore this I can write as modulus a to b fn of t minus f of t, the whole thing into dt. Yes, this is by linearity of the integral of the integral, right? Now those of you who had watched my videos on Riemann integration, you know what it is. This is the basic estimate. This is less than or equal to a to b mod fn t minus f of t dt. You understand? Now is the time we should look at epsilon. Now what is that I wanted to do? I wanted to show this is less than epsilon, this is less than epsilon, but this object is less than or equal to this. Therefore if I show this is less than epsilon, I am through, right? But what is my hypothesis? My hypothesis, fn converges to f uniformly on J. Therefore if you are given me an epsilon, okay, since fn converges to f uniformly on the interval ab, I know there is a capital N, so that for all n greater than or equal to capital N, modulus fn of t minus f of t, and for all t in the interval ab, because uniform convergence is less than epsilon. Yes, therefore if I assume my n is greater than or equal to capital N, this fellow will be less than or equal to a to b, this integrand is less than epsilon into dt. Remember again monotonicity of the integral we are using. What is monotonicity of the integral? If f is less than or equal to g, then integral f is less than or equal to integral g. This is a function as a function of t. This function is less than or equal to the constant function epsilon, right? Therefore integral of this function will be less than or equal to integral of the constant function. You understand? But what is, again we know the definition of, from the definition of integral, this is epsilon into b minus a. You understood that? So what have we shown now? I have shown that if n is greater than or equal to capital N, integral a to b fn of t dt minus integral a to b f of t dt is less than epsilon times b minus a. You understand that? So if you wanted precise epsilon, what do you think I should do? I'll take b minus a. Yeah, you follow that? Okay. So before I stop the lecture, because there is a lot of noise from the children playing, so I do not know whether you also hear that, so it may be a good idea that I stop in time. So let us look at the question. Suppose my f1, again j is an interval. J is an interval? No, I don't want. Okay, j is a subset of R, not necessarily interval, and let's assume they are uniformly continuous on j, and assume f1 converges to f uniformly. What is the question you can ask? Remember, if they are uniformly continuous, they are also continuous, and since f1 converges to f uniformly, I know f is continuous, but f's are uniformly continuous. Therefore I will be curious to know whether f is uniformly continuous. Where? On j. This is a question. Is f uniformly continuous on j? But if you go through the proof, you will see you can prove that. Okay, the first thing where we proved continuity of f, the same proof can be adapted. So I am not going to give complete thing, but let me see. For those of you who have not followed my lectures on uniform continuity, this will be a good thing. To prove if f is uniformly continuous on j, what is that I have to do? Take any 2 points x. So in j, I have to find the estimate for fx minus fy. This is the way I will look at. Okay, I will not say given epsilon choose delta independent of x, not that way. If to check uniform continuity of function on a set, take any 2 points in the set, then look at mod fx minus fy. That you have to find an estimate. Yeah, but as I did earlier, I can do the same thing. Fx minus fy will be less than or equal to fx minus the same. Okay, I will not explain all those things because you should be good at that now, plus fn of f capital N of y minus f of y. Right? By uniform convergence, I can make this epsilon by 3. I can make this less than epsilon by 3. Now, since n is fixed and epsilon by 3 is given, since f1 is also uniformly continuous on j, for any arbitrary x and y in j, what do I know? There is a delta so that x and y belong to j, and mod x minus y is less than delta, should imply mod fn x minus fn y should be less than epsilon by 3. Therefore, what is that I have proved? If fn's are uniformly continuous functions on a set j subset of R, and if fn converges uniformly to f, we already know f is continuous, but we know that f is uniformly continuous. Yeah, please go through the proof. Okay, I'll come back with some more theoretical results which are a little more demanding than what you have done. Yeah, be prepared. Yeah, right. Bye.